Tonight, we drift into the quiet mysteries of the universe. You don't need to follow every word. Just let the story carry you like starlight across a calm sky. As your breathing slows and your thoughts begin to quiet, we'll explore the gentle whispers of cosmic beginnings together. There's no rush, no urgency, only the soft unfolding of ancient light and distant wonder. As evening settles around us, imagine looking up at the night sky. The stars shimmer quietly overhead, each one a tiny island of light in the vast darkness. There's something profoundly calming about stargazing, the way it invites us to breathe more deeply, to settle into a slower rhythm. The night above us holds countless stories written in light, each star a letter in a cosmic alphabet that has been spelling out the universe's secrets for billions of years. Feel the cool night air against your skin as you gaze upward. Perhaps you're lying on soft grass, its gentle tickle against your neck and arms a subtle reminder of Earth beneath you. Or maybe you're wrapped in a warm blanket on a balcony, the day's final warmth still radiating from wooden boards or stone tiles. However you come to this moment of stargazing, allow your body to fully relax, to become heavy and comfortable as your eyes adjust to the darkness above. The longer you look, the more stars appear, pinpricks of light emerging from what at first seemed empty space. Blue-white Sirius, the brightest star in our night sky, perhaps catches your eye first. Then reddish Betelgeuse, the shoulder of Orion. The seven sisters of the Pleiades cluster might appear as a small misty patch. Each of these celestial landmarks has guided human eyes for thousands of years, offering navigation, marking seasons, inspiring stories. When you look at the stars, you're looking at memories, each point of light a moment that happened long ago, traveling across unimaginable distances just to reach your eyes tonight. Some of the starlight touching your face began its journey when dinosaurs still walked the Earth. Other light started traveling before our planet had even formed. The sky is not just a space, but a living history, a gentle archive of time itself. Consider the star Deneb in the constellation Cygnus. Its light takes about 2,600 years to reach us. When the photons now entering your eyes first left that distant sun, the Roman Empire didn't exist. The ancient Greeks were developing early mathematics. Buddha had recently died in India. The light has crossed space unchanged since then, carrying information about a star as it was when human civilization was still in its early chapters. The Andromeda galaxy appears as a faint, misty oval to the naked eye under dark skies. Yet that subtle smudge contains 1 trillion stars, an entire island universe similar to our own Milky Way. The light from Andromeda began its journey 2.5 million years ago, when our early human ancestors were just beginning to use stone tools in the African savanna. That ancient light crosses the void between galaxies, traverses our atmosphere, passes through the pupil of your eye, and forms an image on your retina, connecting you directly to a reality from deep time. Consider how each tiny speck of light represents something that once was everywhere at once. The primordial energy of creation, now condensed into distant suns. The night sky is not merely a scattering of individual lights, but rather the dispersed memory of a time when everything was one. Before stars and planets, before galaxies and nebulae, there was a moment when the entire universe existed in perfect unity. As you breathe slowly beneath the stars, imagine how the hydrogen atoms in every star were created in the first few minutes after the Big Bang. These most basic elements, hydrogen and helium, formed when the universe was still incredibly young. They drifted through space for hundreds of millions of years before gravity gradually pulled them together into the first generation of stars. When you look at starlight, you're seeing these primordial atoms expressing themselves through fusion, releasing energy that has traveled across vast distances just to illuminate your face tonight. The patterns we see among the stars reflect human imagination more than cosmic reality. The stars in any constellation might appear close to one another from our perspective, but in three-dimensional space, they often lie at vastly different distances. Orion's bright shoulder star, Betelgeuse, is about 700 light-years away, while his foot, marked by Rigel, is about 860 light-years distant. We connect these points with invisible lines, creating pictures in the sky that help us remember and navigate. The constellations are a beautiful example of how humans impose meaning on the randomness of nature, finding patterns that help us feel at home in the cosmos. The eye to Ancient Greeks imagined the stars as holes in a great celestial dome, allowing the divine fire beyond to shine through. The Aboriginals of Australia saw them as campfires of ancestral beings. Every culture has looked up with wonder, creating stories to explain the soft lights that punctuate the darkness. And through all these interpretations runs a common thread, a sense that something vast and meaningful surrounds us, holds us, and connects us to everything else. The Maya developed sophisticated astronomical knowledge, tracking Venus with remarkable precision and basing their calendar on careful stellar observations. In China, astronomers recorded supernovae, stellar explosions so bright they became visible in daylight, as early as 1054 CE. The explosion they documented created what we now call the Crab Nebula, a beautiful cloud of expanding gas still visible through telescopes today. The Polynesians navigated thousands of miles of open ocean using their intimate knowledge of the night sky, finding tiny islands with remarkable accuracy in the vast Pacific. These diverse traditions remind us that the human relationship with the stars transcends culture and time. No matter where people have lived, no matter what language they've spoken or stories they've told, they have looked up with the same sense of wonder. The night sky is perhaps our most universal experience, the same stars shining down on every human who has ever lived, connecting us across time and space in a shared contemplation of the cosmos. As you rest, imagine each star as a tiny whisper of the universe's first moment, a cosmic whisper that continues to echo through space and time. The same forces that ignited those distant suns also flow through you. The atoms in your body, the carbon, nitrogen, oxygen, were forged in stellar furnaces billions of years ago. We are in the most literal sense made of stardust. The universe is not something separate from us, but something we are deeply, intrinsically part of. The iron in your blood that carries oxygen to your cells was created in the final explosive moments of massive stars. The calcium strengthening your bones and teeth emerged from similar stellar deaths. The carbon forming the backbone of every protein and cell membrane in your body was fused in stellar cores. Even the gold in jewelry or the silver in electronics came from the most violent cosmic events, neutron star collisions that scattered precious metals across space. When the astronomer Carl Sagan said we are a way for the cosmos to know itself, he was expressing a profound truth. The universe has, through billions of years of evolution, developed consciousness, the ability to reflect on its own existence. Your awareness as you contemplate the stars is the universe contemplating itself. The boundary between you and the cosmos is more permeable than it might first appear, not just philosophically but materially. Your body continuously exchanges atoms with your surroundings. The carbon dioxide you exhale becomes part of plants. The water that passes through you rejoins the hydrological cycle. We are not isolated entities but participants in a continuous exchange of matter and energy. The silence between stars is not empty but filled with invisible connections, gravitational embraces that stretch across light years, quantum entanglements that transcend space itself. Even in the quietest moments, the cosmos hums with unseen relationships, patterns within patterns, connections within connections. Like a sleeping forest that seems still but remains alive with subtle movements, the universe is never truly silent. This cosmic web of relationship extends to the smallest scales. Quantum physics reveals that particles can be entangled in ways that defy our intuitive understanding of space. Two particles, once connected, can instantaneously influence each other's properties, even when separated by vast distances. Einstein called this spooky action at a distance. It suggests that at the deepest level, separateness may be an illusion, that everything remains connected in ways our everyday experience doesn't reveal. Gravitational relationships similarly bind the cosmos together. Each object, from the largest galaxy to the smallest grain of dust, exerts a gravitational influence on every other object. These influences travel at the speed of light, rippling across space-time like waves on a pond. When massive objects collide, they create gravitational waves that compress and stretch space itself as they pass through the cosmos. These waves were first detected in 2015, confirming a prediction Einstein made a century earlier and opening a new way of observing the universe. As you lie beneath the stars, You're held to Earth by the same gravitational force that keeps the Moon in its orbit and binds our solar system together. Gravity is perhaps the most intimate cosmic connection we experience daily, the gentle but persistent embrace between your body and our planet, between Earth and Sun, between our solar system and the galactic center. It's a force both powerful enough to shape the largest structures in the universe and gentle enough that we hardly notice it in our daily lives. When scientists speak of the Big Bang, they often describe it as the beginning of everything, but this isn't quite right. It wasn't the beginning of everything, but rather the beginning of everything as we know it. Space, time, energy, matter. And perhaps the most surprising thing about this cosmic birth is that it didn't happen somewhere in space. There was no somewhere for it to happen in. The Big Bang wasn't an explosion in space. It was an explosion of space itself. The term Big Bang was actually coined somewhat dismissively by astronomer Fred Hoyle, who preferred a different theory of cosmic origins. Yet the name stuck despite being somewhat misleading. There was no bang in the conventional sense, no sound, no shockwave traveling through pre-existing space. Instead, there was a sudden, remarkable expansion of space-time itself from a state of incredible density and temperature. The evidence for this extraordinary event surrounds us. Edwin Hubble's observations in the 1920s revealed that distant galaxies are moving away from us in all directions, with more distant galaxies receding faster, exactly the pattern we would expect if space itself is expanding. The cosmic microwave background radiation, discovered accidentally by Arno Penzias and Robert Wilson in 1964, provides a snapshot of the universe when it was just 380,000 years old. The relative abundance of light elements like hydrogen and helium matches precisely what our models predict would have been created in the first few minutes after the Big Bang. This can be difficult to visualize, like trying to imagine a color we've never seen. Our minds naturally want to picture the Big Bang as a brilliant flash occurring at some specific point, with everything expanding outward from that central location. But the truth is gentler, stranger, and more beautiful. The Big Bang happened everywhere at once because at that moment, everywhere was compressed into a single point. It wasn't that the universe began in one tiny corner of something larger. Rather, all of space, all of possibility, existed in that singular moment. To help visualize this concept, imagine drawing dots on a deflated balloon. As you inflate the balloon, every dot moves away from every other dot. No dot is at the center of this expansion. The center is inside the balloon, not on its surface. Similarly, our three-dimensional space might be thought of as the surface of a four-dimensional expansion, with no center located within the space itself. Another helpful visualization is to think of a loaf of raisin bread dough rising in an oven. Each raisin moves away from every other raisin as the dough expands. From the perspective of any single raisin, it appears that all other raisins are moving away from it. No raisin is at the center. The expansion happens throughout the entire volume of dough. If you were somehow able to witness this beginning, you wouldn't see it from the outside looking in. There was no outside. You would be the beginning, experiencing the birth of distance itself, the first separation of here from there. Imagine being inside a balloon as it inflates, except the balloon isn't expanding into anything. The balloon itself is all that exists, and its surface is growing from within. The term Big Bang suggests something violent and loud, but perhaps it would be more accurate to think of it as the universe's first breath, a gentle unfurling of possibility. In those earliest moments, there was no sound because sound requires air and there was no air yet. There was no color because light, as we know it, had not yet formed. There was only potential, condensed and perfect, beginning to express itself. In the first fraction of a second, about 10 or 43 seconds after the beginning, a period called the Planck era, our current understanding of physics breaks down entirely. This is the domain where quantum gravity would operate, a theory we haven't yet fully developed. This earliest moment remains veiled in mathematical mystery, a reminder that our knowledge, while vast, still has fundamental limits. By about 10 to 36 seconds, the universe entered a phase called cosmic inflation, an extraordinarily rapid expansion that stretched space itself by a factor of at least 10^26 in just a tiny fraction of a second. This expansion smoothed out irregularities, and established the remarkably uniform background we observe today. It also expanded quantum fluctuations into the seeds that would eventually grow into galaxies and galaxy clusters. As the inflation period ended, the energy that had driven this expansion was converted into particles and radiation in a process physicists call reheating. The universe was now filled with an incredibly hot, dense plasma of fundamental particles, quarks, electrons, photons, and more exotic particles now seen only in our most powerful particle accelerators. Before this moment of cosmic birth, time itself did not exist in any way we can comprehend. There was no before the Big Bang in any meaningful sense, just as there is no north of the North Pole. Time began when space began. They are woven together in what physicists call space-time, an integrated fabric that forms the foundation of our reality. Einstein showed us that time and space are not separate things, but different aspects of the same underlying reality. This concept challenges our intuition, which is built from everyday experiences where time seems to flow independently of space. But Einstein's theories of relativity revealed that time and space are intimately connected. Time passes differently depending on your speed or your proximity to massive objects. An observer moving at high speed will measure time passing more slowly than one at rest. Similarly, time flows more slowly and stronger. Gravitational fields, a clock on Earth's surface, runs slightly slower than one in orbit. These effects are tiny in our everyday experience but become significant at extreme speeds or in intense gravitational fields. Near a black hole, for instance, time can dilate dramatically. What would be years for a distant observer might be just minutes for someone falling toward the event horizon. These aren't just theoretical predictions. They've been confirmed by precise atomic clocks on aircraft and satellites. Imagine time not as a steady tick-tock of seconds, but as a soft river flowing through the landscape of space. At the moment of the Big Bang, this river began its journey. The first moments were unlike any we can experience now. Time itself was compressed, flowing differently in the incredible density of the early universe. As space expanded, time stretched and settled into the rhythm we now experience. As you rest and listen, feel your own experience of time, how it seems to flow at different rates depending on your state of mind. When deeply relaxed or absorbed in something beautiful, time often seems to expand, to move more slowly and spaciously. This subjective experience of time reminds us that even in our personal consciousness, time is not the rigid, mechanical progression we often imagine it to be. Those initial instants after the Big Bang unfolded, like the opening notes of a cosmic symphony, each moment giving birth to the next in a seamless progression. From pure energy emerge the first fundamental forces, gravity separating first, then the strong nuclear force followed by the weak nuclear force and electromagnetism. The universe was learning its own nature, discovering the rules that would govern everything to come. At first, the four fundamental forces existed as a single, unified force, a perfect symmetry that would gradually break as the universe cooled, like ice crystals forming in water as temperature drops. Gravity was the first to separate, becoming distinct when the universe was just 10.43 seconds old. The strong nuclear force, which holds atomic nuclei together, separated next. By about 10.12 seconds, the electromagnetic and weak nuclear forces had also become distinct, establishing the four fundamental interactions that govern all physical processes we observe today. This gradual breaking of symmetry, this differentiation of forces, represents a kind of cosmic maturation, the universe evolving from perfect unity toward the complex, differentiated state that allows for structure and life. It's a pattern we see repeated throughout nature. From simplicity emerges complexity, from uniformity emerges diversity, from potential emerges expression. For a brief, extraordinary period, the entire cosmos was smaller than an atom, denser than anything we can imagine, and hotter than any star. Yet within this seemingly chaotic state lay perfect mathematical precision, the fundamental constants of nature being established with exquisite accuracy. Had any of these values been slightly different, our universe would have evolved along entirely different lines, perhaps never developing stars, planets, or the complex chemistry necessary for life. The precise value of these constants, the strength of gravity, the charge of an electron, the mass of fundamental particles, seems finely tuned to allow for a universe that can develop complexity. If gravity were slightly stronger, stars would burn out too quickly for life to evolve. If the strong nuclear force were slightly weaker, atoms beyond hydrogen couldn't form. This apparent fine-tuning has led some physicists to propose the anthropic principle, the idea that we observe these particular values precisely because they're the ones that allow observers like us to exist. Others suggest that perhaps our universe is just one of many in a vast multiverse, each with different physical constants. In this view, we naturally find ourselves in a universe with life-permitting values, just as fish naturally find themselves in water rather than on land. These different interpretations remind us that at the boundary of physics and cosmology, we encounter questions that blend into philosophy, questions about purpose, meaning, and our place in the cosmos. As the universe expanded and cooled, it passed through phase transitions, similar to how water changes from steam to liquid to ice. Each transition marked a fundamental shift in how energy and matter interacted. About 1 second after the beginning, protons and neutrons formed. A few minutes later, the first atomic nuclei emerged, primarily hydrogen and helium with traces of lithium. But the universe was still too hot for these nuclei to capture electrons and form complete atoms. That would come much later. During this period of nucleosynthesis, roughly from 10 seconds to 20 minutes after the Big Bang, the universe was essentially a nuclear fusion reactor. The conditions were perfect for assembling the nuclei of the lightest elements. About 75% of the matter became hydrogen nuclei, single protons, while most of the remainder became helium nuclei, 2 protons and 2 neutrons. Trace amounts of deuterium, heavy hydrogen, and lithium also formed. It's remarkable to consider that the hydrogen in water, in oceans, clouds, and within your own body was created during these first few minutes of cosmic existence. Every time you drink water, you're consuming atoms that have existed since the universe was less than half an hour old. There's something profoundly connecting in this realization that the most common element in the universe and a key component of life links us directly to the cosmic dawn. This early universe wasn't expanding into anything. There was no outside for it to expand into. Rather, it was expanding into itself, creating more space with each passing moment. Every point in the universe was moving away from every other point, like dots on the surface of an inflating balloon. There was no center to this expansion, because every location could equally claim to be the center from its own perspective. This concept of expansion without edges challenges our spatial intuition. We naturally want to imagine the universe as a giant sphere growing into some larger space. But the mathematics of general relativity describes a space that is either infinite and growing, or finite but without boundary, like the surface of a higher dimensional sphere. In either case, there is no edge, no boundary where the universe ends and something else begins. If you could somehow travel in a straight line through space for an infinite amount of time, you would never reach a cosmic border or edge. In a finite universe without boundary, you might eventually return to your starting point, having circumnavigated the cosmos like a sailor circling the globe. In an infinite universe, you would simply continue forever, encountering new regions of space without limit. As you rest and listen, try to feel the gentle rhythm of your breathing, the expansion and contraction that sustains you. In some small way, this mirrors the universe's own breathing, its own pattern of expansion. The cosmos continues to grow not with force or effort, but with a kind of effortless inevitability, following the path established in those first moments. Your breath moves in and out approximately 20,000 times each day, usually without conscious direction. Similarly, the universe expands according to its intrinsic nature, following patterns established in its earliest moments. There's something deeply reassuring about this cosmic breathing, its steadiness, its reliability, its gentle persistence. The universe doesn't struggle to expand any more than you struggle to breathe when relaxed and at ease. The expansion of the universe isn't like ordinary movement through space. It's more like the stretching of space itself. Imagine a cosmic tapestry, infinitely large and infinitely detailed. Now imagine this tapestry slowly stretching in all directions, each thread moving away from every other thread. The patterns on the fabric, galaxies, clusters, superclusters, All maintain their internal integrity while the distances between them gradually increase. This stretching of space affects light traveling through the cosmos in a fascinating way. As light moves through expanding space, its wavelength gets stretched, shifted toward the red end of the spectrum in what astronomers call redshift. The further light has traveled, the more space has expanded during its journey, and the greater its redshift. By measuring this redshift, astronomers can determine how far away distant objects are and how fast they're moving away from us. The most distant galaxies we can observe are receding at over 90% of the speed of light. Their light so dramatically redshifted that what began as ultraviolet or visible light reaches us as infrared or radio waves. These distant galaxies appear to us not as they are now, but as they were billions of years ago, when the universe was much younger. Observing them is like reading a cosmic history book, each page showing an earlier chapter in the universe's development. This cosmic fabric, what scientists call space-time, learned to move in those earliest moments. It's not solid or static, but dynamic and flowing. Einstein showed us that massive objects create curves in this fabric, like heavy balls placed on a trampoline, and these curves guide the motion of other objects. The planets orbit the sun not because they're pulled by some mysterious force, but because they're following the natural contours of space-time created by the sun's mass. That Einstein's insight represented a profound shift in our understanding of gravity. Before relativity, scientists viewed gravity as a force acting between objects with mass. Einstein revealed that gravity is actually the effect of curved space-time on the motion of objects. Mass tells space-time how to curve, and curved space-time tells matter how to move. This elegant formulation explains why all objects fall at the same rate, regardless of their mass. They're simply following the same space-time contours. In 2015, scientists directly detected ripples in this cosmic fabric, gravitational waves produced by the collision of two black holes 1.3 billion light-years away. These waves, predicted by Einstein a century earlier, compressed and stretched space-time by a tiny amount as they passed through Earth. Their detection required instruments of extraordinary precision, capable of measuring changes smaller than the width of a proton. These gravitational waves open a new window on the universe, allowing us to hear cosmic events that may not be visible through conventional astronomy. There's something deeply soothing about contemplating this cosmic fabric. Unlike our daily lives with their sharp edges and abrupt transitions, space-time flows and bends with mathematical elegance. Stars and planets move along the paths of least resistance, following the gentle undulations of this universal medium. Even light itself, the fastest thing in existence, obediently follows these curves, sometimes bending around massive objects like galaxies, in what we call gravitational lensing. This bending of light by gravity creates some of the most beautiful phenomena in astronomy. Massive galaxy clusters can act as cosmic magnifying glasses, focusing and brightening the light from more distant galaxies behind them. These gravitational lenses sometimes create multiple images of the same background galaxy, or stretch its appearance into long, curved arcs. Through these effects, we can observe galaxies so distant and faint they would otherwise be completely invisible to us. Another way the universe reveals its hidden depths through the mathematics of curved space-time. As you relax and breathe deeply, imagine yourself floating in this cosmic fabric, held in its gentle embrace. There's no effort in this floating, just as celestial bodies effortlessly follow their orbital paths. The mathematics of space-time provides a kind of cosmic choreography, guiding the dance of stars and planets with perfect precision. There's beauty in this mathematical elegance, a beauty that transcends our everyday understanding of physics and connects to something deeper, a harmonious order underlying the apparent complexity of the cosmos. As the universe continued to expand and cool, it passed through a moment of profound significance about 380,000 years after the Big Bang, when it had cooled enough for electrons to combine with nuclei, forming the first complete atoms. This moment, called recombination, marked the point when light could finally travel freely through space. Before this, photons were constantly being absorbed and re-emitted, bouncing between the densely packed charged particles. After recombination, light could stream unimpeded across the cosmos. Before recombination, the universe was opaque, filled with a hot, dense plasma that scattered light in all directions, rather like a dense fog. As the temperature dropped below about 3000 Kelvin, approximately 5000 degrees Fahrenheit, electrons could remain bound to nuclei without being immediately knocked loose by energetic photons. As electrons combined with nuclei to form neutral atoms, the fog suddenly cleared. Photons, no longer constantly scattered by free electrons, could travel in straight lines across the expanding universe. This transition happened remarkably quickly by cosmic standards. Over a period of just a few thousand years, the universe transformed from opaque to transparent. It was as though a cosmic curtain was drawn back, allowing light to shine through the darkness for the first time. This moment represents a kind of cosmic dawn, not the first light, which had existed since the earliest moments, but the first light that could travel freely, illuminating the newly transparent cosmos. This first free light still exists today, stretched by the expanding universe into microwave wavelengths. We call it the cosmic microwave background radiation, a faint, almost perfectly uniform glow that fills the entire sky in every direction. It's the oldest light in the universe, the most distant thing we can observe, a gentle echo of creation itself. If you could see microwaves, the entire night sky would glow with this ancient light, a soft reminder of the universe's fiery youth. The cosmic microwave background was discovered accidentally in 1964 by radio astronomers Arno Penzias and Robert Wilson. They detected a persistent background noise in their antenna that they initially thought was caused by pigeon droppings interfering with their equipment. After cleaning their antenna and ruling out other possible sources, they realized they had stumbled upon something profound, the thermal radiation left over from the Big Bang itself. This ancient light has been studied in extraordinary detail by satellites like COBE, WMAP and Planck. These observations reveal tiny temperature fluctuations, variations of just 1 part in 100,000, that correspond to regions of slightly different density in the early universe. These minute variations were the seeds from which all cosmic structure would eventually grow. The slightly denser regions attracted more matter through gravity, eventually forming galaxies and galaxy clusters, while less dense regions evolved into the cosmic voids we observe today. The cosmic microwave background radiation provides the strongest evidence we have for the Big Bang theory. Its near-perfect uniformity confirms that the entire observable universe was once in a hot, dense state. The pattern of its tiny fluctuations matches precisely what our models predict from quantum fluctuations in the earliest moments, expanded to cosmic scales by inflation. It's as though the universe has preserved a perfect baby picture of itself, a snapshot from when it was just 380,000 years old, in a history spanning 13.8 billion years. There's a beautiful symmetry in the idea that the universe has no center, or rather, that every point is equally central to the cosmic story. From any galaxy in the universe, observers would see the same essential picture, everything moving away from them, with more distant objects receding faster. This doesn't mean each observer is at the true center of expansion. It simply reflects the nature of how space itself expands, this cosmic democracy, where no location is privileged over any other, stands in stark contrast to earlier models of the universe. Ancient cosmologies typically placed Earth at the center of creation, with celestial bodies revolving around us in perfect circles. The Copernican revolution began the gradual displacement of humanity from this central position, showing that Earth orbits the Sun rather than vice versa. Later discoveries revealed that our Sun is just one of billions of stars in the Milky Way galaxy, and our galaxy just one of billions in the observable universe. Each of these discoveries has expanded our perspective, revealing a cosmos far larger and more intricate than previously imagined. Yet rather than diminishing humanity's significance, this cosmic context invites a deeper appreciation of our unique position. We exist in a universe vast enough to develop galaxies, stars, and planets, and on at least one of those planets, life has evolved sufficient complexity to comprehend its own cosmic origins. We may not be at the physical center of the universe, but we are a way for the universe to know itself. Imagine a loaf of raisin bread rising in an oven. Each raisin moves away from every other raisin as the dough expands. From the perspective of any single raisin, It appears to be at the center of this expansion. But there is no center, just the uniform expansion of the dough itself. Our universe works in much the same way, with galaxies playing the role of raisins in the cosmic dough. This lack of a true center gives the universe a profound democracy. No place is more special or privileged than any other. Earth isn't at the center of creation, nor is our Milky Way galaxy, nor our local group of galaxies, nor even our supercluster. We exist within an unimaginably vast cosmos, where every location is equally ancient, equally born from that first moment. Consider that light from the cosmic microwave background reaches us from all directions equally. This perfect spherical symmetry around us might suggest we're at a special location, the center of this radiation sphere. But observers in the Andromeda galaxy, 2.5 million light-years away, would see exactly the same thing: cosmic microwave background radiation reaching them from all directions. This is only possible if the radiation fills all of space uniformly, with no central point of origin. There's something deeply calming about this cosmic perspective. The pressures and urgencies of daily life fade against the backdrop of universal expansion. The universe unfolds according to its nature, without haste or delay, each moment flowing into the next with perfect continuity. As you listen to these words, perhaps drifting in and out of awareness, the cosmos continues its gentle breathing all around you. This cosmic perspective can bring a sense of peace to our daily concerns. The deadlines, the worries, the small frustrations that sometimes feel all-consuming, all exist within this vast, expanding cosmos that has unfolded over billions of years. This doesn't mean our human experiences don't matter. Rather, it places them in a context that can sometimes help us approach them with greater equanimity, with a more spacious awareness. Between the galaxies lies what we might call cosmic silence, vast regions of seemingly empty space that separate the luminous islands of stars. But this silence is not truly empty. It contains extremely rarefied gas, invisible dark matter, and the ever-present cosmic microwave background radiation. These intergalactic spaces are the universe's quiet places, where the density of matter drops to just a few atoms per cubic meter. The intergalactic medium consists primarily of hydrogen and helium gas at extraordinarily low densities, typically just 1 atom per cubic meter, compared to about 1025 molecules per cubic meter in Earth's atmosphere at sea level. This rarefied gas exists at a wide range of temperatures, from a few thousand to millions of degrees Kelvin, depending on its proximity to galaxies and its history of heating and cooling. Within these vast, nearly empty regions, there are filaments of slightly denser gas that trace the cosmic web, the large-scale structure that organizes galaxies into clusters, filaments and walls surrounding relatively empty voids. This cosmic web forms a kind of skeleton for the universe, guiding where matter gathers and where it doesn't, like the veins of a leaf or the branches of a tree. The similarity between these cosmic patterns and biological structures isn't merely poetic, it reflects how similar mathematical principles can generate comparable forms at vastly different scales. There's something meditative about contemplating these vast, quiet spaces. Like the pauses between musical notes that give shape to a melody, the emptiness between galaxies gives structure to the universe. Without these expanses, the cosmos would be a uniform blur rather than the beautiful clustering of stars and galaxies we observe. The emptiness is not nothing. It is the canvas upon which the universe paints its most magnificent structures. In music, silence is as important as sound. The spaces between notes allow each note to be heard distinctly rather than blending into noise. Similarly, the vast spaces between galaxies allow cosmic structure to develop and be observed. If matter were distributed uniformly throughout the universe, there would be no galaxies, no stars, no planets, no possibility for the complex chemistry that supports life. The emptiness is not a lack but a necessity, an essential component of cosmic architecture. And within this apparent stillness, incredible motions are taking place. Galaxies are not fixed in position, but are flowing along cosmic currents, drawn by the gravitational pull of matter we cannot see. Great walls and filaments of galaxies stretch across billions of light-years, forming a cosmic web that resembles neurons in a vast brain or the branching pattern of leaves on a tree. Nature repeats its favorite forms across all scales, from the microscopic to the cosmic, The Sloan Great Wall, for example, is a filament of galaxies stretching more than 1.4 billion light-years across space. The Boötes void is an enormous cosmic bubble, nearly 330 million light-years in diameter, containing remarkably few galaxies. These structures, among the largest known in the universe, emerged from those tiny quantum fluctuations present in the earliest moments after the Big Bang, amplified by inflation and gradually enhanced by gravity over billions of years. The movement of galaxies reveals another cosmic mystery: dark matter. By observing how galaxies rotate and how they move within clusters, astronomers have determined that the visible matter we can see accounts for only about 15% of the total matter in the universe. The remainder consists of dark matter, a substance that doesn't interact with light, but exerts gravitational pull on ordinary matter. This invisible component shapes the cosmic web, forming gravitational scaffolding that guides the formation and movement of galaxies. As the universe expands, these structures grow more distant from one another, but their internal connections remain. Gravity binds galaxies together in clusters, clusters into superclusters, creating a hierarchy of relationship that resists the overall cosmic expansion. It's as though the universe maintains different rhythms simultaneously: the grand expansion of space itself, and the local gathering of matter through gravitational attraction. Our Milky Way galaxy, for instance, is gravitationally bound to the Andromeda galaxy and about 50 smaller galaxies in what we call the local group. This galactic neighborhood will remain together despite cosmic expansion. So in fact, the Andromeda galaxy is actually moving toward us rather than away. We will collide and merge in about 4.5 billion years, forming a new, larger galaxy sometimes called Milkomeda. This future merger reminds us that the cosmos continues to evolve and change, with new structures forming even as space expands. The local group itself is part of the Virgo supercluster, which in turn is part of an even larger structure called the Laniakea supercluster, a vast collection of 100,000 galaxies spanning 520 million light-years. These nested relationships, these hierarchies of cosmic structure, demonstrate how gravity creates order within the expanding universe, like eddies forming within a flowing river. Perhaps the most surprising aspect of cosmic expansion is that we cannot feel it. The universe grows, yet our world stays still, untouched by the stretching of space. This is because the expansion primarily affects the largest scales, the distances between galaxy clusters. Within galaxies like our Milky Way, gravitational bonds are strong enough to overcome the expansion effect. Our solar system, our planet, our bodies all remain the same size because the forces holding them together are far stronger than cosmic expansion. The expansion of space itself exerts no force in the conventional sense. It doesn't pull or push on objects. It simply increases the distance between points in space that aren't bound together by other forces. Electromagnetic forces hold atoms and molecules together. Nuclear forces bind protons and neutrons in atomic nuclei. These forces are overwhelmingly stronger than the effect of cosmic expansion at such small scales. Even at the scale of our solar system, the gravitational bonds between the Sun and planets easily overcome any expansive tendency of space itself. The distance between Earth and the Sun isn't increasing due to cosmic expansion. It's determined entirely by conventional gravitational physics. Similarly, the Milky Way galaxy maintains its size and structure through the gravitational attraction between its stars and the presence of dark matter, completely unaffected by the expansion of the universe. Imagine sitting in a quiet meadow, watching clouds drift overhead. You don't feel the Earth spinning at over 1,000 miles per hour. You don't feel our planet's orbit around the Sun at 67,000 miles per hour. You don't feel our solar system's motion around the galactic center at 514,000 miles per hour. And you certainly don't feel the expansion of the universe. We live within nested layers of motion, each imperceptible to our senses, yet fundamentally shaping our reality. There's something wonderful about this, the way we can be simultaneously at rest and in motion, depending on the reference frame. Your body might feel completely still as you relax, yet you're participating in multiple cosmic motions. Similarly, at the deepest level of awareness, You might experience both profound stillness and the constant flow of sensations, thoughts, and feelings. This paradox, stillness within movement, movement within stillness, appears throughout nature. From subatomic particles to cosmic expansion, there's comfort in knowing that the universe expands without disrupting the delicate structures that make life possible. Stars continue their steady fusion. Planets maintain their orbits. The intricate dance of atoms and molecules proceeds undisturbed. The cosmic expansion affects only the vastest scales, leaving our local neighborhood, even our entire galaxy, essentially unchanged. This pattern, where large-scale expansion coexists with local stability, reflects a beautiful balance in cosmic architecture. If expansion affected small scales, atoms would be pulled apart, molecules would dissociate, and complex structures like stars, planets, and living organisms could never form. If gravitation were too strong relative to expansion, the entire universe might have recollapsed shortly after the Big Bang. The actual balance allows for both the growth of the cosmos as a whole and the formation of structured complexity within. And as the early universe expanded and cooled, another profound transition occurred, the gradual shift from perfect order toward increasing complexity. In the first instance after the Big Bang, the cosmos existed in a state of extraordinary simplicity and uniformity. Energy was distributed almost perfectly evenly throughout space, with only the tiniest quantum fluctuations disturbing this perfect symmetry. These quantum fluctuations, microscopic variations in energy density, were artifacts of the Heisenberg uncertainty principle, a fundamental feature of quantum mechanics. This principle states that certain pairs of properties, like position and momentum or energy and time, cannot both be precisely determined simultaneously. These tiny uncertainties, present even in the vacuum of space, became the seeds from which all cosmic structure would eventually grow. During the inflation period, that brief but extraordinary expansion early in the universe's history, these quantum fluctuations were stretched from subatomic scales to macroscopic scales. What began as minute variations in energy density became slight differences in the distribution of matter across vast regions of space. In regions with slightly higher density, gravity could begin its work of drawing matter together, initiating the long process that would eventually form galaxies and stars. But as time passed, these tiny irregularities began to grow. Slightly denser regions attracted more matter through gravity, becoming even denser, while less dense regions became emptier. This process, the growth of structure from nearly perfect smoothness, represents entropy's first footstep in the cosmic story. Entropy is a concept from thermodynamics that measures the number of different ways the microscopic components of a system can be arranged while producing the same macroscopic state. High entropy corresponds to many possible microscopic arrangements, what we often call disorder. Low entropy corresponds to few possible arrangements, what we might call order or organization. The second law of thermodynamics states that in an isolated system, entropy always increases over time. The early universe, with its nearly uniform distribution of energy, was in a state of remarkably low entropy. This might seem counterintuitive. A smooth, uniform gas might appear disordered to our eyes, but from a statistical perspective, a perfectly uniform distribution is extremely unlikely and represents a highly ordered state. There are far more ways for particles to be clumped together in some regions and spread out in others than for them to be distributed with perfect uniformity. Entropy is often described as a measure of disorder, but perhaps it's better understood as a measure of possibility. The early universe, in its extraordinary uniformity, had very low entropy, very few possible arrangements of its components. As structure developed, as matter clumped into galaxies and stars, the number of possible arrangements increased enormously. Entropy grew, and with it grew the richness and complexity of cosmic architecture. This growth of entropy, this movement from the improbable uniformity of the early universe toward the more probable state of clustered matter, provides the arrow of time. Unlike the equations of fundamental physics, which work equally well forward or backward in time, the second law of thermodynamics distinguishes past from future. Time flows in the direction of increasing entropy, from states of lower probability toward states of higher probability. Yet this increasing entropy doesn't mean the universe simply becomes more chaotic or disordered in the conventional sense. Within the overall trend toward higher entropy, local reductions in entropy can occur. Stars, planets, and living organisms represent local decreases in entropy, highly organized systems that develop and maintain their structure by exporting entropy to their surroundings. Life itself might be understood as a process that creates and maintains local order while increasing the entropy of the wider environment. There's something deeply poetic about this transition from perfect simplicity to beautiful complexity. It's as though the universe needed to break its initial symmetry to create anything interesting. The perfect plasma of the early cosmos could never have developed planets, chemistry, or life. It was the gentle growth of non-uniformity, the subtle triumph of difference over sameness that allowed for the rich tapestry of existence we now observe. There's something deeply poetic about this transition from perfect simplicity to beautiful complexity. It's as though the universe needed to break its initial symmetry to create anything interesting. The perfect plasma of the early cosmos could never have developed planets, chemistry, or life. It was the gentle growth of non-uniformity, the subtle triumph of difference over sameness, that allowed for the rich tapestry of existence we now observe. As you breathe slowly and deeply, consider how this cosmic principle of symmetry breaking mirrors the rhythm of your own breath, the continuous alternation between inhalation and exhalation, the gentle oscillation between opposing states that sustains life itself. In perfect uniformity, there would be no change, no flow, no possibility. It is the breaking of perfect balance that creates movement. That generates the currents of existence in which life can emerge and flourish. Look around you, if your eyes are open, or simply feel the space around you if they're closed. Notice how everything you perceive embodies this principle of broken symmetry. The irregular patterns in wood grain, the asymmetrical arrangement of furniture in a room, the complex whirls of your own fingerprints. Perfect symmetry, while mathematically beautiful, would leave no space for the wonderful variability that makes our world so rich and engaging. This cosmic journey from simplicity to complexity mirrors many patterns we see in nature. A single cell divides and specializes to create the intricate structure of a living organism. A uniform cloud of gas collapses and differentiates to form a solar system with distinct planets. Even human creativity often involves breaking symmetry, introducing variation into uniformity to create meaning and beauty. Consider the development of an embryo, beginning as a single fertilized cell with near-perfect symmetry, then dividing, differentiating, folding upon itself to create the extraordinary complexity of a human being, with trillions of specialized cells working in harmony. This process follows the same fundamental pattern as cosmic evolution, starting with simplicity and, through a series of symmetry-breaking transitions, developing into organized complexity. Similarly, musical compositions often begin with a simple theme that gradually develops through variations, harmonizations, and counterpoints into rich tapestries of sound. A single melody becomes a symphony through the skilled introduction of difference within sameness, variation within repetition. The composer, like the universe itself, creates beauty by breaking perfect uniformity and exploring the vast space of possibilities that opens up. In painting, too, perfect symmetry often feels static and lifeless, while slight asymmetries create dynamic tension and visual interest. The greatest artists understand intuitively that beauty emerges not from perfect balance, but from the tension between order and variation. Just as the cosmos finds its expression not in uniform plasma, but in the dance of galaxies, stars, and planets that emerged from tiny quantum fluctuations in the early universe. As you rest and listen, consider how your own existence represents an extraordinary arrangement of matter, a temporary pattern of exquisite complexity. Your body contains around 30 trillion cells, each with its own internal structure and function. The atoms in your body were forged in stars that died billions of years ago, releasing their elemental treasures into space. These atoms have been recycled countless times through geological processes, through other living things, before becoming, for this brief moment, you. Every atom in your body is in constant motion, electrons orbiting nuclei at tremendous speeds, molecules vibrating and rotating, cells renewing themselves through continuous cycles of construction and demolition. Your body replaces most of its atoms every few years, yet you maintain a continuous sense of identity. You are not so much a fixed object as a pattern that persists through constant material change, a standing wave in the river of cosmic matter and energy. The complexity of a single living cell exceeds our full comprehension. Thousands of proteins, folded into precise three-dimensional shapes, interacting through biochemical pathways of stunning intricacy. Each cell in your body contains about 2 meters of DNA, tightly coiled within its nucleus, a molecular library containing instructions that, if printed in books, would fill a small room. Yet this is just one cell among trillions that together form the community of cells that is you. This extraordinary complexity doesn't exist in isolation, but is nested within larger systems of complexity. You within a family or community, within a society, within the biosphere of Earth, within the solar system, within the Milky Way galaxy, within a universe that spans billions of light years. Each level of organization follows similar patterns, with simpler components arranging themselves into more complex wholes through the gentle guidance of fundamental forces. There's a profound connection between human existence and cosmic origin. We are quite literally made of star stuff. The iron in your blood, the calcium in your bones, the carbon in your cells, all were created through nuclear fusion in the hearts of stars or during their explosive deaths. When you look at your hand, you're seeing elements that didn't exist in the early universe, but had to be manufactured through stellar processes over billions of years. The iron atoms in your hemoglobin, carrying oxygen through your bloodstream right now, were likely formed during the explosive death of a massive star that lived and died long before our solar system formed. In the intense heat and pressure of a supernova, atomic nuclei are fused into heavier elements like iron, which are then scattered across interstellar space. These elemental treasures eventually became incorporated into new star systems, including our Sun and its family of planets. The calcium strengthening your bones and enabling your muscles to contract was also forged in stellar furnaces. Without these stellar contributions, your body could not exist. You are, in the most literal sense, assembled from the remnants of ancient stars, cosmic recycling at its most profound and beautiful. Your atoms have existed since nearly the beginning of time, taking different forms through the ages, now temporarily arranged in the unique pattern that is you. Even your consciousness, that remarkable capacity for self-awareness and reflection that allows you to contemplate these cosmic connections, emerges from the interaction of atoms and molecules arranged in patterns of extraordinary complexity. The same fundamental forces that govern stellar fusion and planetary formation also guide the electrochemical processes in your brain, creating the continuous stream of awareness that you experience as your conscious life. Our atoms remember the first light of creation. They carry within them the history of cosmic evolution, from the pure energy of the Big Bang, through the formation of the first elements, the birth and death of stars, the assembly of our solar system, and the long development of life on Earth. We are not separate from this cosmic story, but an integral part of it, a way for the universe to experience itself, to know itself, to reflect on its own existence. When you gaze at the stars, it is not just you observing them. It is also the elements forged in stars observing their distant cousins across the vastness of space. There's a profound circularity in this relationship, stars creating the elements that eventually develop consciousness capable of contemplating the stars. The universe has developed eyes to see itself, a mind to comprehend its own existence. This perspective dissolves the sharp boundary we often place between ourselves and the cosmos. You are not in the universe. You are the universe, a particular expression of cosmic processes, a localized pattern of matter and energy that has temporarily taken the form of a conscious being. Your thoughts, your feelings, your awareness, these are not separate from the cosmos, but are modes of cosmic expression, ways that the universe experiences itself subjectively. The atoms flowing through your body will eventually return to the cosmic cycles from which they came. The carbon, oxygen, nitrogen, and other elements that form your body will one day be released back into the Earth's systems, perhaps becoming part of other living beings, perhaps drifting through oceans or atmosphere, perhaps eventually being drawn into the formation of new stars and planets in the distant future when our sun has completed its life cycle. Some cosmologists have proposed that our universe might be just one of many, perhaps infinitely many, universes existing together in what we call the multiverse. Like soap bubbles floating in an unseen sea, countless Big Bangs might be blooming across a larger reality that we cannot directly observe. Each universe might have different physical laws, different fundamental constants, different possibilities for complexity and life. The concept of a multiverse emerges naturally from several theoretical frameworks in modern physics. Inflationary cosmology suggests that the rapid expansion that occurred in the earliest moments of our universe's history continues eternally in other regions, creating new bubble universes with potentially different properties. String theory, which attempts to unify quantum mechanics and general relativity, suggests a vast landscape of possible universes, perhaps 10,500 different possible configurations of the fundamental constants. Imagine these universes as parallel realities, each with its own cosmic history unfolding according to its particular physical laws. Some might collapse almost immediately after formation. Others might expand so rapidly that atoms never form. Still others might develop physics so different from our own that we can barely conceptualize what structures might emerge. And perhaps some, like our own, have just the right balance of forces to allow for the development of complexity, chemistry, and eventually consciousness. This multiverse concept invites us to imagine our cosmos as an infinite bubble, vast beyond comprehension from within, yet possibly finite and bounded when viewed from some higher perspective we cannot access. Our observable universe, the part we can see, extends about 46 billion light-years in every direction. But this may be just a tiny fraction of the total extent of our universe, which could be infinitely large or simply much larger than what we can observe. The cosmic horizon that limits our vision is not a physical boundary, but an observational one. We cannot see beyond it, because light from more distant regions hasn't had time to reach us since the Big Bang. This horizon surrounds every observer in the universe, moving with them like a bubble of visibility in a much larger cosmos. What lies beyond our horizon is likely similar to what lies within it: more galaxies, more stars, more planets, extending perhaps infinitely, or perhaps eventually reconnecting with itself. In a closed geometry that defies our everyday spatial intuition, there's something soothing about contemplating these nested scales of existence, the way our seemingly boundless cosmos might itself be just one bubble in a greater sea. It reminds us that there are always larger contexts, wider perspectives, more encompassing frameworks for understanding. No matter how far our knowledge extends, there remains the possibility of something beyond, something more. This humility before the unknown is central to both scientific inquiry and spiritual contemplation. Both recognize that our understanding is always provisional, always incomplete, always open to revision in light of new experience or insight. The vastness of the multiverse concept reminds us not to confuse our maps with the territory they represent. Our theories, models, and concepts are useful tools for navigation, but the reality they attempt to describe always exceeds our conceptual grasp. The concept of multiple universes might seem purely speculative, beyond any possibility of scientific verification. Yet theoretical physics has been led to this idea through rigorous mathematical analysis, particularly through string theory and inflationary cosmology. The same equations that successfully describe our observable universe naturally suggest the existence of others. The multiverse isn't merely philosophical conjecture, but a serious scientific hypothesis, albeit one that remains challenging to test. Some cosmologists have suggested that we might find indirect evidence for other universes. If our universe once collided with another, it might have left subtle patterns in the cosmic microwave background radiation. Or perhaps the particular values of fundamental constants in our universe make more sense when viewed as one possibility among many in a vast ensemble of universes, each with different physical properties. These approaches transform what might seem like untestable metaphysics into potentially observable science. The Multiverse concept also offers a possible explanation for the apparent fine-tuning of our universe, the way fundamental constants seem precisely calibrated to allow for the emergence of complexity in life. If there are infinitely many universes with different properties, then it's not surprising that we find ourselves in one that permits our existence. This anthropic reasoning doesn't explain why the multiverse exists, but it does help explain why we observe the particular cosmic parameters that we do. As you drift with these thoughts, there's no need to fully grasp or visualize these concepts. Let them wash over you like gentle waves, carrying your awareness beyond the boundaries of everyday thinking. The multiverse theory offers not answers but beautiful questions, an invitation to wonder about what might exist beyond the limits of our cosmic horizon. Within our universe, time flows in one direction, from past to future, never reversing. This asymmetry, what physicists call the arrow of time, is intimately connected to the concept of entropy we explored earlier. As the universe evolves from ordered simplicity toward complex possibility, it creates a direction for time itself. We remember the past, but not the future, because entropy increases in one direction only. This asymmetry of time presents one of the deepest puzzles in physics. The fundamental laws of physics, whether classical mechanics, electromagnetism, or even quantum mechanics, are essentially time-symmetric. If you were to watch a movie of elementary particles interacting and then see the same movie played backward, both versions would appear to follow the same physical laws. Yet at the macroscopic level, we observe a clear distinction between past and future. Eggs break but don't unbreak. Coffee cools but doesn't spontaneously heat up. People age but don't grow younger. This emergence of temporal asymmetry from apparently symmetric laws relates to probability and statistics. While it's not impossible for heat to flow from cold to hot, or for shattered glass to reassemble itself, such events are so extraordinarily improbable that we never observe them in practice. The arrow of time points in the direction of increasing probability, from less likely arrangements toward more likely ones, from order toward equilibrium. Imagine stirring cream into coffee. The swirling patterns are beautiful and complex, but they're also irreversible. You cannot unstir the coffee, separating the cream back into its original state. This simple everyday observation reflects a profound cosmic principle. Processes that increase entropy can occur spontaneously, while processes that decrease entropy generally cannot. The arrow of time points in the direction of increasing entropy. As you watch cream and coffee mix, you're observing the same principle that drives cosmic evolution, the tendency of closed systems to evolve from less probable states toward more probable ones. The initial state, cream and coffee separated, is highly ordered and improbable from a statistical perspective. The final state, a uniform mixture, represents the most probable arrangement of cream and coffee molecules, the state with the highest entropy. This principle operates at all scales throughout the universe. Stars burn their nuclear fuel and eventually die because energy tends to disperse from concentrated to diffuse forms. Galaxies evolve from more ordered states toward more disordered ones, though this process unfolds over billions of years rather than minutes. Even the universe as a whole follows this pattern, evolving from the extraordinarily low entropy state of the Big Bang toward states of ever-increasing entropy. Yet within this overall trend toward increasing entropy, remarkable structures can emerge. Living organisms maintain their internal order by exporting entropy to their surroundings, taking in low-entropy energy, like sunlight or food, and releasing higher-entropy waste heat and compounds. These islands of local order, these temporary reversals of the entropic trend, don't violate the second law of thermodynamics, but rather exemplify how complex systems can develop within its constraints. Yet the cosmos still remembers its timeless infancy. The cosmic microwave background radiation preserves a record of the universe when it was just 380,000 years old, a mere infant in cosmic terms. By studying this ancient light, scientists can peer back toward the beginning, measuring the conditions that existed long before stars or galaxies had formed. It's as though the universe keeps a baby photo of itself, accessible to anyone with the right instruments to observe it. This cosmic microwave background was discovered accidentally in 1964 by radio astronomers Arno Penzias and Robert Wilson, who detected a persistent noise in their antenna that couldn't be eliminated. What they had stumbled upon was the thermal radiation left over from the early universe, light that had been traveling through space since atoms first formed, stretched by cosmic expansion from visible light to microwave wavelengths. Their discovery, which earned them the Nobel Prize in Physics, provided the strongest evidence for the Big Bang theory. The cosmic microwave background radiation appears remarkably uniform across the entire sky. Its temperature varies by only about 1 part in 100,000 from one direction to another. These tiny variations, first measured precisely by the COBE satellite in the early 1990s, represent small differences in density in the early universe, the seeds from which all cosmic structure would eventually grow. By mapping these minute temperature differences, scientists can reconstruct the conditions present in the infant universe with extraordinary precision. Each fluctuation in this ancient light represents a region that would eventually evolve into a galaxy cluster or cosmic void. The slightly denser regions attracted more matter through gravity, becoming increasingly dense over time, while less dense regions became progressively emptier. This process of gravitational amplification transformed tiny quantum fluctuations, random variations caused by the Heisenberg uncertainty principle, into the vast cosmic structures we observe today. There's something deeply moving about this cosmic memory, the way information from the earliest moments continues to travel through space, reaching us billions of years later. Nothing is ever truly lost in the cosmos. It just becomes more difficult to reconstruct. The universe preserves its history within its structure, like growth rings in an ancient tree or layers in geological strata. The light from the cosmic microwave background has been traveling for 13.8 billion years before reaching our telescopes. During this immense journey, it has passed through developing cosmic structures, galaxy clusters, filaments, and voids, carrying subtle imprints of these encounters. By analyzing these imprints, scientists can map the distribution of matter between us and the cosmic background, creating a kind of cosmic tomography that reveals the universe's large-scale structure. This preservation of information extends to other aspects of cosmic structure. The relative abundance of elements in the universe, roughly 75% hydrogen, 25% helium, and traces of lithium, matches precisely what nuclear physics predicts would have been created during the first few minutes after the Big Bang. This elemental signature has remained largely unchanged over cosmic history, providing another window into the universe's earliest moments. Even the patterns of galaxy distribution contain echoes of the universe's infancy. Subtle acoustic oscillations, pressure waves that move through the hot plasma of the early universe, left their mark as a characteristic length scale in the distribution of galaxies. By measuring this scale at different cosmic epochs, scientists can track how the universe has expanded over time, providing some of our strongest evidence for dark energy and the accelerating expansion of space. As the universe expanded from its initial singularity, another force was quietly at work, shaping everything that would follow. Gravity, the gentle pull that attracts all matter toward all other matter, sculpted the cosmos into the structures we see today. While it's the weakest of the 4 fundamental forces, gravity's influence extends across unlimited distances, making it the dominant force on the largest scales. Gravity is perhaps the most familiar force in our daily experience. It keeps our feet on the ground, causes raindrops to fall, and gives weight to our bodies. Yet it's also the force we understand least completely from a theoretical perspective. Einstein's general relativity describes gravity not as a force in the conventional sense, but as a curvature of space-time caused by mass and energy. This geometric understanding of gravity has been confirmed by numerous observations, from the bending of starlight around the sun to the precise timing of binary pulsars. Despite its relative weakness, gravity is about 1040 times weaker than the electromagnetic force. Gravity shapes the largest structures in the universe through its cumulative effect over vast distances. While electromagnetic forces tend to cancel themselves out, positive charges attracting negative ones, creating neutral systems, gravity always attracts and never repels. allowing its influence to build up over astronomical scales. Imagine gravity not as a forceful push or pull, but as a patient sculptor, slowly gathering matter into increasingly complex arrangements. In the early universe, regions with slightly more matter attracted additional material, growing over time into the vast filaments of the cosmic web. Within these filaments, matter condensed further to form galaxies, great, spiraling disks or elliptical clouds, containing hundreds of billions of stars. This cosmic web, the large-scale structure of the universe, resembles a sponge or foam, with galaxies concentrated along filaments that surround vast, nearly empty voids. Computer simulations of cosmic evolution, starting with the tiny fluctuations observed in the cosmic microwave background and following how gravity would shape them over billions of years, produce structures remarkably similar to what we actually observe through telescopes. This agreement between theory and observation confirms our understanding of how gravity shapes the universe on the largest scales. The dance of attraction that formed these structures wasn't violent or sudden, but unfolded over billions of years. Gravity works without haste, without rest, a consistent presence guiding cosmic evolution. It's the slow heartbeat of creation, the rhythmic pulse that brings order to chaos without disrupting the overall expansion of space. There's something deeply reassuring about gravity's patient work, the way it gathers and organizes without force or struggle. Stars form not through sudden collapse, but through gradual condensation, as gravity slowly overcomes the outward pressure of gas and radiation. Galaxies interact not through violent collisions, but through extended gravitational dialogues, often spiraling around each other for billions of years before merging. Even black holes, perhaps the most dramatic manifestations of gravity's power, form and grow through processes that unfold over cosmic timescales. Within galaxies, gravity continued its creative work, collapsing vast clouds of hydrogen and helium to form the first stars. The earliest stars were giants, perhaps hundreds of times more massive than our Sun, with correspondingly brief lifespans. They burned hot and fast, fusing hydrogen and helium into heavier elements before exploding as supernovae, scattering these new elements across space. These first stars, sometimes called population 3 stars, formed about 100 to 250 million years after the Big Bang. They contained only the primordial elements, hydrogen, helium, and traces of lithium, with essentially no heavier elements. Because of this primitive composition and their immense mass, they evolved differently from modern stars, burning brighter and hotter, completing their life cycles in just a few million years rather than the billions of years that stars like our Sun endure. We've never directly observed these first-generation stars. They're too distant and existed too briefly in the cosmic past. But their explosive deaths must have been among the most energetic events in cosmic history, briefly outshining entire galaxies. These explosions enriched the surrounding gas with the first heavy elements, carbon, oxygen, silicon, iron, setting the stage for the formation of more complex chemistry, planets, and eventually life. These first stellar explosions represent a kind of second birth for the universe, the quiet fire of stars kindling again, the spark of that original cosmic explosion. In the heart of every star, conditions briefly resemble the early universe. Extreme heat and pressure forcing atomic nuclei to overcome their natural repulsion and combine. Stars are cosmic alchemists, transmuting simple elements into more complex ones through the alchemy of nuclear fusion. In the core of a star like our Sun, temperatures reach about 15 million degrees Celsius, and pressures exceed 200 billion times Earth's atmospheric pressure at sea level. Under these extreme conditions, hydrogen nuclei, protons, can overcome their mutual electrical repulsion and approach closely enough for the strong nuclear force to bind them together, forming helium and releasing energy in the process. This energy flows outward through the star's layers, eventually reaching the surface and radiating into space as light and heat. More massive stars can achieve even higher core temperatures and pressures, allowing them to fuse helium into carbon, carbon into oxygen, and so on up to iron. Each fusion step requires more extreme conditions and releases less energy, creating a nested onion-like structure within the star, with the heaviest elements concentrated toward the center. Elements heavier than iron cannot be created through fusion that releases energy. Their formation requires energy input, which occurs primarily during supernova explosions. Our own sun continues this ancient process, converting about 600 million tons of hydrogen into helium every second. The energy released in this transformation is what warms our planet, grows our food, and ultimately makes all life possible. We are, in a very real sense, children of starlight, our existence dependent on this quiet stellar fire that has burned across cosmic time. Every plant that grows on Earth's surface captures energy that began its journey in the sun's core, traveling as photons across 93 million miles of space before being transformed through photosynthesis into the chemical energy that powers the biosphere. When you eat a piece of fruit or a vegetable, you're ingesting solar energy that has been temporarily stored in chemical form. When you burn wood in a fireplace, you're releasing sunlight that was captured by a tree decades or centuries ago. Even fossil fuels, coal, oil, and natural gas represent ancient sunlight, captured by plants hundreds of millions of years ago and preserved underground through geological processes. By burning these fuels, we're releasing energy that originated in the sun's core in the distant past. In this sense, almost all the energy that powers human civilization, whether from renewable or non-renewable sources, can be traced back to the nuclear fusion occurring in our parent star. There's a beautiful continuity between the Big Bang and the stars that followed billions of years later. The same fundamental forces, the same physical laws that governed the universe's first moments, continue to operate in stellar cores today. It's as though the cosmos is still creating itself, still expressing the potential inherent in that initial singularity through the birth and death of countless stars. This continuity extends to the physical constants that determine how these forces operate: the strength of gravity, the charge of an electron, the masses of fundamental particles. These values were established in the earliest moments of cosmic history and have remained unchanged throughout the universe's evolution. Stars form and function according to the same physics that governed the primordial fireball, just operating under different conditions of temperature and density. The elements created in stellar furnaces, carbon, oxygen, nitrogen, and others essential for life, retain the properties they had when first forged. A carbon atom created in a star 10 billion years ago behaves identically to one created in a laboratory today. This consistency, this reliability of natural law across cosmic time and space, is what allows us to study distant stars and galaxies with confidence that the same physics applies there as here. As you rest and listen to these words, consider that the light warming your skin during daylight hours comes from a star, our sun, while the light that guides us at night comes from many more distant stars. We live our lives bathed in starlight, surrounded by the gentle radiance of cosmic furnaces, both near and unimaginably far. The photons touching your skin began their journey about 8 minutes ago in the sun's photosphere, the visible surface layer from which light finally escapes after a much longer journey from the core. These photons were created deep in the sun's interior, perhaps thousands of years ago, gradually working their way outward through successive layers of increasingly transparent gas before breaking free into space and racing toward Earth at the speed of light. At night, the starlight reaching your eyes has traveled much further. The light from even the closest star, Proxima Centauri, takes over 4 years to reach Earth. Most of the stars visible to the naked eye lie within a few hundred to a few thousand light-years of our solar system, just a tiny neighborhood within our galaxy, which spans about 100,000 light-years from edge to edge. Yet even this limited sample of stars shows remarkable diversity, different sizes, colors, temperatures, and ages, from newly formed stars still surrounded by their birth clouds to ancient red giants nearing the end of their lives. When we gaze at the night sky, we encounter a beautiful paradox. What we see is not what is, but what was. Light from even the nearest star, Proxima Centauri, takes over 4 years to reach us. The bright star Sirius appears to us as it was 8.6 years ago. The Andromeda Galaxy, visible as a faint smudge to the naked eye, shows us light that began its journey 2.5 million years ago when our human ancestors were first learning to use stone tools. This delay in light's arrival means that we're always looking into the past when we look outward in space. If Betelgeuse, a massive red supergiant star in the constellation Orion, were to explode as a supernova today, We wouldn't know about it for about 550 years, until the light from that explosion finally reached Earth. Similarly, if intelligent beings on a planet 100 light-years away were observing Earth right now, they would be seeing our world as it was in 1925, with no knowledge of subsequent history. This observer's paradox means that every gaze into the sky is also a gaze into the past. Each photon arriving at your eye is a time traveler, bringing information from a moment long gone. The further we look into space, the further we look back in time, until at the very limits of our observation, we see the cosmic microwave background, light from the universe, when it was just beginning to become transparent. Astronomers leverage this relationship between distance and time to study cosmic evolution. By observing galaxies at different distances, and therefore different look-back times, they can trace how galactic structures have changed over the universe's history. Nearby galaxies show us recent cosmic history, while the most distant observable galaxies reveal conditions as they were billions of years ago, when the universe was just a fraction of its current age. The most distant galaxies we can observe appear to us as they were less than 1 billion years after the Big Bang, still in their formative stages, smaller and more irregular than modern galaxies, often undergoing intense bursts of star formation. By comparing these early galaxies with more mature ones observed at intermediate distances, astronomers have pieced together the evolutionary history of galactic development, how small, primitive galaxies merged and grew into the majestic, spiral and elliptical galaxies that populate the universe today. There's something profoundly calming about this perspective, the way it gently dissolves our usual understanding of now. When astronomers observe a supernova in a distant galaxy, they're not seeing something that's happening simultaneously with their observation. They're witnessing an echo from the deep past, an event that might have occurred before humans existed, its light only now completing its long journey across space. This cosmic perspective on time can help us relate differently to our own temporal existence. Just as there is no universal now in the cosmos, no single moment that all observers would agree is the present, perhaps we can hold our own experiences of time more lightly, recognizing that our sense of urgency, of the pressing now, is partly a construction of consciousness rather than an absolute reality. The universe unfolds across billions of years. Perhaps we can allow ourselves to breathe more deeply into a wider temporal perspective. This connection between distance and time creates what we call our observable universe, the spherical region, centered on Earth, from which light has had time to reach us since the Big Bang. Beyond this cosmic horizon lie parts of the universe we cannot see, not because they don't exist, but because their light hasn't had enough time to reach us. The universe is likely much larger than what we can observe. Perhaps infinitely large, our observable universe extends about 46 billion light-years in all directions, considerably larger than the 13.8 billion light-years you might expect given the universe's age. This discrepancy arises because space itself has been expanding while light travels through it. The most distant objects we can see today are now much farther away than when they emitted the light we're receiving, having been carried further away by cosmic expansion during light's journey toward us. This cosmic horizon isn't static, but expands as the universe ages, gradually encompassing more of the total cosmos. With each passing year, light from slightly more distant regions has had time to reach us, expanding our observable bubble slightly. Yet the acceleration of cosmic expansion means that some regions of the universe will remain forever beyond our observation. Light emitted from those regions now will never reach us, no matter how long we wait, because the stretching of intervening space happens faster than light can cross it. The illusion of distance begins to dissolve when we truly grasp this relationship between space and time. What we call far away might really mean long ago. The edge of our observable universe isn't primarily a boundary in space but in time. We can't see beyond it because we can't see before the beginning of our universe. Space and time are not separate dimensions, but aspects of a single unified fabric. Einstein's special and general theories of relativity formalized this unification of space and time into space-time. Special relativity showed that observations of distance and duration vary depending on relative motion. Fast-moving observers measure distances to be contracted and time to be dilated compared to stationary observers. General relativity extended this insight to show how mass and energy curve spacetime, creating what we experience as gravity. Perhaps the most profound implication of relativity is that there is no absolute, universal present moment, no cosmic now that all observers would agree upon. What one observer considers simultaneous events, another observer moving at a different velocity would experience as occurring at different times. This relativity of simultaneity fundamentally challenges our intuitive understanding of time as flowing uniformly throughout the universe. As you drift with these thoughts, imagine the vast network of light rays crisscrossing the cosmos, each one carrying information, each one connecting distant points in both space and time. You, sitting or lying here now, are the recipient of light that has traveled across billions of years, from sources that might no longer exist as they appeared when they emitted that light. There's something beautiful about being this kind of cosmic receiver, a consciousness aware of its place in the great web of space-time. The photons entering your eyes have traversed the vacuum of space, passed through Earth's atmosphere, and activated photoreceptors in your retina, triggering electrochemical signals that your brain interprets as images. This seemingly simple act of seeing connects you directly to distant cosmic events, making you a participant in an exchange of information that spans both space and time. Your awareness of the night sky is not separate from the cosmic process, but an integral part of it, the universe perceiving itself through the temporary arrangement of matter that is you. In a sense, all of us exist in what we might call an endless now, a present moment that contains within it echoes of the distant past and seeds of the far future. The Big Bang isn't just something that happened 13.8 billion years ago. Its effects continue to unfold all around us. The expansion of space continues. The cosmic microwave background radiation continues to wash over us. The elements forged in that initial creation and in subsequent stars continue to form the substance of our world. When you drink a glass of water, you're consuming hydrogen atoms created in the Big Bang itself. When you breathe, you're exchanging oxygen atoms forged in the hearts of ancient stars. When you look at your hand, you're seeing carbon atoms that once existed in other forms, perhaps in prehistoric plants, in the bodies of dinosaurs, in the shells of ocean creatures that formed limestone deposits. Nothing material is truly new. Everything is recycled from what came before, participating in a continuous cosmic dance of transformation. This continuity of matter through time means that you share atoms with all that has ever existed on Earth. Some of the atoms in your body almost certainly once belonged to ancient organisms, to extinct species, to historical figures. There's a material connection linking you to all of Earth's past, a connection that extends further back to stellar processes and ultimately to the Big Bang itself. Some physicists have suggested that from a four-dimensional perspective, one that views time as just another dimension like space, the entire history of the universe exists as a complete object, sometimes called the block universe. In this view, the Big Bang isn't something that happened once and is now over, but rather the edge of a four-dimensional structure that encompasses all of space-time. Past, present, and future all exist simultaneously in this perspective, with our consciousness simply moving through this pre-existing terrain. This block universe concept emerges naturally from relativity theory. Just as all points in space exist, regardless of where we happen to be located, perhaps all moments in time exist regardless of which moment we happen to be experiencing as now. Our sense of the present moment moving through time might be more a feature of consciousness than a fundamental aspect of reality, a particular way of experiencing a four-dimensional reality that itself doesn't flow or change. Interestingly, this view aligns with certain philosophical and spiritual traditions that speak of experiencing life from outside of time, seeing past, present, and future as aspects of a single, unified reality rather than as a sequence of separate moments. Mystics across various traditions have reported experiences of transcending ordinary temporal awareness, accessing a perspective where time appears different, more unified, less linear, less constraining. There's something deeply meditative about this view of time, the way it invites us to see beyond the apparent flow of moments into a more comprehensive understanding where everything is, connected across time as well as space. The beginning and the end exist together, and our journey from one to the other is more about perspective than about actual change. This perspective doesn't invalidate our everyday experience of time passing, but offers a complementary view, one that might help us hold our temporal existence more lightly. The urgencies that often drive our daily lives appear different when considered from this more spacious perspective. The pressing deadlines, the anxious anticipations, the regretful ruminations about the past all exist within a larger context where time itself has a different quality. Whether or not this block universe perspective is physically correct, it offers a calming metaphor for how we might relate to time in our own lives. The urgent now that often consumes our attention exists within a much larger context, a complete story that connects what came before us with what will come after. Our present moment is not isolated, but woven into the full tapestry of time. As we contemplate the distant future of our cosmos, we encounter a vision both peaceful and melancholy, the universe falling asleep. Current observations suggest that the expansion of space is not slowing down, but actually accelerating, driven by a mysterious force scientists call dark energy. If this acceleration continues, galaxies will eventually move beyond each other's cosmic horizons, becoming permanently invisible to one another. This accelerating expansion was discovered in 1998 through observations of distant supernovae, earning the scientists involved the Nobel Prize in Physics. These observations showed that very distant supernovae appeared dimmer than expected, indicating that the expansion of space has been speeding up rather than slowing down over the past several billion years. This discovery fundamentally changed our understanding of cosmic destiny, from a universe that might eventually recollapse or expand at an ever-diminishing rate to one that will expand ever faster, driven by dark energy. Dark energy remains one of the greatest mysteries in modern physics. It appears to be a property of space itself, a kind of negative pressure or tension that causes space to expand at an accelerating rate. It comprises about 68% of the total mass energy content of the universe, with dark matter making up about 27% and ordinary matter, the stuff of stars, planets and living beings, accounting for just 5%. This means our familiar world represents just a tiny fraction of cosmic reality, with the vast majority consisting of components we can detect only indirectly, through their gravitational effects. In this far future, trillions of years from now, each galaxy or local cluster of galaxies will appear to be alone in an otherwise empty universe. Stars will have exhausted their fuel. Black holes will have evaporated through Hawking radiation. Even atoms may eventually decay. The cosmos will approach a state of maximum entropy, what physicists call the heat death of the universe. This heat death doesn't mean high temperature, but rather thermal equilibrium, a state where energy is distributed so uniformly that no further work can be extracted, no further structure can emerge. Without temperature differences, no heat engines can operate. Without energy gradients, no complexity can be maintained. The universe would reach a kind of perfect stillness, not empty, but filled with an extremely diffuse gas of elementary particles at a temperature infinitesimally above absolute zero, with no structure or organization. Before reaching this final state, the cosmos would pass through several distinct epochs. In about 100 billion years, all galaxies outside our local group would have receded beyond our observable horizon, making the observable universe appear to contract rather than expand. In about 100 trillion years, star formation would cease as the available gas becomes exhausted. The remaining stars would gradually burn out, leaving only stellar remnants, white dwarfs, neutron stars, and black holes. Over much longer timescales, 10-40 years or more, even these remnants would decay. Protons might decay into lighter particles. Black holes would gradually evaporate through Hawking radiation. Eventually, only extremely low-energy radiation would remain, with the cosmos approaching a state of maximum entropy and perfect equilibrium. A quiet ending to the cosmic story that began with the Big Bang. Yet there's a strange peace in this distant cosmic twilight. The universe will not end in violence or catastrophe, but in a kind of quiet completion. energy dispersed evenly throughout space, no more work possible, no more structure emerging. Like a story that has expressed all it needed to express, the cosmos will rest in perfect equilibrium. This vision of cosmic quietude has parallels in various spiritual and philosophical traditions, the concept of nirvana in Buddhism, for instance, or the heat death in thermodynamics. Both point to a state beyond striving, beyond the tension of opposites, beyond the push and pull of becoming. There's a kind of ultimate peace in this completion, not an empty void, but a fullness that contains all possibilities in perfect balance. This vision of cosmic quietude invites us to appreciate the extraordinary moment we inhabit, a time when stars still shine, when galaxies still dance in gravitational embrace, when complexity and life are possible. We exist during what might be called the universe's biological age, the relatively brief period when conditions allow for the emergence and flourishing of complex structures. Like living organisms, the conditions that make life possible are remarkably specific. Temperatures low enough for complex chemistry, but high enough for liquid water. Elements beyond hydrogen and helium, available from previous generations of stars. A stable planetary environment, protected from cosmic radiation and impacts. These conditions haven't always existed and won't persist indefinitely. We inhabit a special moment in cosmic history when the universe has cooled sufficiently from its fiery beginning but hasn't yet dissipated into its cold conclusion. This temporal specialness complements the spatial specialness we've already discussed, the Goldilocks zone around our sun where temperatures allow for liquid water, the galactic habitable zone, where star formation and supernova rates create favorable conditions for life. We exist in a kind of sweet spot in both space and time, a region of the cosmos where complexity can flourish, where consciousness can emerge, where the universe can develop the capacity to contemplate its own existence. As you rest and listen, there's no need to fear this distant future. It lies so far ahead that it exceeds not just human timescales, but the lifespans of stars and galaxies. And who knows what new understandings might emerge in the meantime. Perhaps what seems like an ending from our current perspective will appear as a transition when viewed through the lens of future knowledge. The history of cosmology reminds us how dramatically our understanding can change over time. A century ago, scientists believed the Milky Way constituted the entire universe. 70 years ago, the Big Bang theory was still controversial. 30 years ago, the existence of planets around other stars remained unconfirmed. 25 years ago, the acceleration of cosmic expansion hadn't yet been discovered. Our current models, while supported by substantial evidence, remain works in progress, approximations, of a reality that likely exceeds our current conceptual frameworks. Perhaps future discoveries will reveal possibilities beyond the heat death, cyclic models where our universe gives birth to new universes, mechanisms for cosmic renewal that reset entropy, connections to other dimensions or realities that change our understanding of cosmic destiny. The recognition of our limited knowledge invites both scientific humility and a sense of wonder at what remains to be discovered. We might find comfort in seeing the universe as an unfolding dream, one that began with the Big Bang and continues to express itself through every cosmic process, every galactic evolution, every planetary formation, every emergence of life and consciousness. We are within this dream, part of its ongoing creativity, expressions of its inherent potential. This metaphor of a cosmic dream invites us to consider the universe not as a machine, deterministic and mechanical, but as a creative process, continually bringing forth new forms, new possibilities, new expressions. Like a dream that generates its own content, the cosmos seems to possess an intrinsic creativity, a capacity to develop increasingly complex structures and relationships from simpler beginnings. The dream that never ended flows through all things, through distant quasars and neighboring trees, through ancient light and tomorrow's sunrise. The same fundamental patterns, the same physical laws that shaped the earliest moments of creation continue to operate in every falling leaf, every ocean wave, every human heartbeat. The universe is not something that happened long ago. It is something that is happening now, in and through, and as everything that exists. When a wave forms in the ocean, it's not separate from the water. It's a pattern of movement within the water itself. Similarly, everything we identify as a distinct object or entity, a planet, a person, a thought, might be understood as a pattern within the underlying fabric of the cosmos. We are not things within the universe, so much as processes of the universe, temporary forms that the cosmic reality takes as it explores its own creative potential. There's a profound unity in this perspective, a recognition that beneath the apparent diversity and separation of the world lies a continuous process that connects all things across both space and time. The hydrogen atoms in water molecules throughout your body were created in the first few minutes after the Big Bang. The carbon, nitrogen, oxygen, and other heavier elements were forged in stellar furnaces. You are not just connected to the cosmic story. You are an expression of it, a way that the universe experiences itself. This understanding doesn't diminish the uniqueness of your individual existence, but places it within a larger context that gives it additional meaning and significance. Your consciousness, your capacity for wonder, your ability to contemplate the cosmos. These are not separate from the universe, but ways that the universe has developed to explore its own nature. When you ponder the stars, it is the universe pondering itself, through the particular arrangement of matter and energy that is you. This perspective aligns with insights from various wisdom traditions that speak of an underlying unity beneath apparent diversity, the Vedantic concept of Brahman, the Taoist notion of the way, the Christian mystic sense of divine omnipresence, the Buddhist understanding of dependent origination. These traditions, while differing in important details, point toward a similar recognition that separation is in some sense illusory, that everything is interconnected within a deeper wholeness. As our journey together comes to a close, let's return to where we began, the quiet contemplation of the night sky. Those distant stars, those ancient lights, continue their silent witness whether we observe them or not. The cosmos unfolds according to its nature, expanding, creating, dissolving, renewing, in an endless cycle that began with the first moment and continues through this very breath you're taking now. As your breathing slows and deepens, imagine your consciousness expanding beyond the boundaries of your body, beyond the confines of this moment, to embrace the vastness of space and time. Feel yourself as both infinitesimally small within the cosmic expanse and infinitely significant as a conscious participant in the universe's unfolding. Both perspectives are true, both are valuable. The cosmic and the personal existing not in opposition, but in complementary relationship. The stars will shine long after we are gone, their light crossing endless space. But tonight they shine here with you in silence. May your evening be calm and your rest be deep. The universe holds you in its gentle embrace, just as it holds every galaxy, every planet, every living thing. You are home in this cosmos, a welcome participant in the grand unfolding that began 13.8 billion years ago and continues, moment by moment, in perfect rhythm with your own existence. As your awareness drifts towards sleep or deeper relaxation, trust that the same cosmic processes that create and sustain the stars also create and sustain you. There's nothing to grasp, nothing to achieve, only this moment of being, this participation in the cosmic dance that needs no explanation or justification beyond itself. Rest now in this awareness, in this belonging, in this gentle communion with all that is, has been, and will be. Good night, cosmic traveler. Sleep well beneath the ancient stars.